Many people probably think climate is just a simple sum of weather. It rains today. It's sunny tomorrow. And it's windy the day after. These scattered meteorological events, when combined, make up the climate. But in reality, the climate system is far more complex than that. It is a massive network composed of the oceans, the atmosphere, land, ice sheets, and the biosphere working together. Every single part is constantly exchanging information with the others, transferring energy, and influencing one another. Just imagine, if we compare the Earth to a human body, then the atmosphere is like our skin and hair. It's the part we perceive most easily. The weather forecasts we watch every day are actually just reporting the state of the atmosphere. But inside this body, there are even larger systems at work. The ocean is like the Earth's circulatory system. It covers 71% of the Earth's surface, absorbing the vast majority of solar radiation that reaches the planet, and redistributing that heat across the globe through ocean currents. The atmosphere is like the respiratory system, transporting heat from the oceans in the form of water vapor, latent heat, and other means to every corner of the globe. The land is like the bones and muscles. Its terrain and landscape determine the direction in which wind and water flow. Ice sheets act as a regulator. When the Earth warms up, the melting ice absorbs heat. When the Earth cools down, the expanding ice reflects more sunlight. These systems are tightly linked through physical, chemical, and biological processes, forming an extremely complex feedback network. A change in wind direction in one place might, a few days later, affect rainfall in another part of the world. A shift in the temperature of a stretch of ocean could potentially, months later, reshape the entire atmospheric circulation pattern of a hemisphere. El Niño is one of the most critical anomaly signals within this system. To understand El Niño, we first need to grasp a key concept: trade winds. Trade winds are constant, prevailing winds in the atmosphere. In the equatorial region, they blow from east to west, like a conveyor belt that never stops. Under normal conditions, the strong southeast trade winds continuously push surface seawater off the coast of South America toward the west, causing warm surface water to pile up in the western Pacific. Meanwhile, in the eastern Pacific, because the surface water is blown away, deep, cold water upwells to replace it, resulting in relatively lower water temperatures. This seemingly simple interaction between wind and ocean actually harbors tremendous energy. As warm seawater accumulates in the western Pacific, the air there warms up and rises, forming a low-pressure zone. With relatively cooler seawater in the eastern Pacific, the air there sinks, forming a high-pressure zone. Air flows from the high-pressure zone toward the low-pressure zone, creating the trade winds we mentioned earlier at low altitudes, while a reverse airflow forms at high altitudes. This circulation loop is known as the Walker circulation. It is one of the most important circulation patterns in the atmosphere-ocean system. In a normal year, the Walker circulation brings abundant rainfall to the western Pacific region, and maintains the unique climate patterns of places like Southeast Asia and Australia. But every few years, this tranquil system is thrown into chaos. The trade winds suddenly weaken, or even change direction entirely. Warm surface water is no longer pushed toward the western Pacific. Instead, it begins to flow back toward the east. Sea temperatures in the eastern Pacific rise abnormally, and the rainfall belt shifts eastward as well, impacting the climate of the entire Pacific, and indeed, the globe. The entire landscape would be completely rewritten by this anomaly. This is what we call El Niño. From a scientific perspective, El Niño is an abnormal state of the ocean atmosphere coupled system. To be more precise, when the sea surface temperature in the central and eastern equatorial Pacific is more than 0.5 degrees Celsius above the long-term average. And this anomaly persists for more than 5 months. It is officially classified in meteorology as an El Niño event. This definition might sound highly technical, but the implications behind it are profound. It tells us that El Niño is not just a simple weather phenomenon. Rather, it is a persistent state of anomalous sea temperatures. It doesn't just affect the weather for a day or two. It causes shifts in the entire climate pattern over timescales, lasting several months or even over a year. Why is it the 0.5 degree mark? After long-term research, scientists discovered that this threshold is a critical turning point. Sea temperature fluctuations below this magnitude are quite common in nature and are considered normal year-to-year variations. But once it exceeds this threshold, it triggers a series of positive feedback mechanisms, causing the abnormal state to amplify and persist, ultimately leading to significant changes in the global climate landscape. How exactly is El Niño formed? This is a question that has puzzled scientists for decades. And there are still many mysteries yet to be solved. However, we have now come to understand some of the key mechanisms. First, there is the anomaly of the trade winds. In a normal year, strong trade winds act like an invisible hand, pushing warm surface water toward the west. But in an El Niño year, this hand suddenly grows weak. The strength of the trade winds diminishes, and sometimes they even briefly reverse into westerly winds. The cause of this change may be related to temperature changes in the Indian Ocean, or seasonal oscillations within the tropical atmosphere. It could also be linked to large-scale ocean fluctuations. But as for what specifically triggers it, scientists are still looking into that. When the trade winds weaken, the warm water that had been pushed to the west begins to break free. It rushes back eastward like a herd of wild horses running free. This warm water piles up in the eastern Pacific, causing an abnormal rise in sea temperatures there. At the same time, the usually strong cold water upwelling in the eastern Pacific weakens or even stops. This further intensifies the rise in sea temperature. So, what are the consequences of rising sea temperatures? As we know, there is a constant heat exchange between the ocean and the atmosphere. A rise in sea temperature means the ocean releases more heat and moisture into the atmosphere. This causes the atmosphere above the sea surface to become hotter, more humid, and more unstable. Convective activity increases, and rainfall becomes more frequent. The latent heat released by that rainfall then further heats the atmosphere, altering the temperature structure and pressure distribution of the air. Changes in pressure distribution then feed back to affect wind patterns. The trade winds that once blew toward the western Pacific are weakened, or might even turn into westerly winds. And these changes in the trade winds further impact ocean currents, causing even more warm water to shift eastward. And just like that, a positive feedback loop is formed. Once an El Niño begins, it reinforces itself, and is very difficult to stop. Mentioning El Niño, we have to mention its little sister, La Niña. La Niña means little girl in Spanish, acting as the counterpart to the Christ child. These two phenomena are like the two extreme states of our climate system. La Niña occurs when sea surface temperatures in the central and eastern equatorial Pacific are more than 0.5 degrees Celsius below the long-term average. During a La Niña year, the trade winds become exceptionally strong, pushing even more warm water toward the western Pacific. While sea temperatures in the eastern Pacific remain abnormally low, the water circulation is stronger than in a normal year. This means there is more rainfall in the western Pacific, making it more prone to flooding, while in the eastern Pacific and South America, the west coast becomes much drier. Historically speaking, El Niño and La Niña tend to alternate, forming an oscillation with a cycle of about 2 to 7 years. This cycle is known as the El Niño Southern Oscillation. or ENSO for short. ENSO is the most intense interannual climate variability signal on Earth. Its impact spans the entire globe, profoundly shaping the climate patterns of continents and the development trajectory of human civilization. It is worth noting that ENSO is not a perfectly regular cycle. Sometimes it occurs for 2 consecutive years. Sometimes there are long gaps between occurrences. Sometimes the intensity is very high, and other times it is relatively mild. This irregularity increases the difficulty of prediction, and is also one of the challenges in climate science research. Research in recent years indicates that El Niño is not a single phenomenon, but can be divided into at least 2 different types. The first type is called Eastern Pacific El Niño, also known as conventional El Niño. It is characterized by the most significant sea surface temperature anomalies occurring in the eastern part of the equatorial Pacific, which is near the coast of South America. This type of El Niño has been more common throughout history, and is also easier to observe. The second type is called Central Pacific El Niño, also known as Dateline El Niño. Its characteristic is that the area with the most significant sea temperature anomalies is located in the central equatorial Pacific, roughly near the international dateline. This type of El Niño seems to have become more frequent in recent decades. Although these 2 types of El Niño differ in their sea surface temperature distribution, both have significant impacts on the global climate. It is just that the specific patterns of their impact and the severity can vary quite a bit. For example, the impact of the Central Pacific El Niño on the Indian monsoon may differ from that of the Eastern Pacific type, and the effects on China's climate might also vary. There is also another important question. What is the relationship between El Niño and global warming? Looking at long-term trends, global warming is changing the fundamental state of our oceans and atmosphere. Ocean temperatures are rising overall, and the moisture content in the atmosphere is increasing. All of these factors could influence the frequency and intensity of El Niño events. Some research suggests that, as global warming intensifies, extreme El Niño events might become more frequent. Additionally, climate change could cause certain characteristics of the ENSO cycle to shift. Some studies have shown that, in recent decades, the peak intensity of El Niño events may have increased, and their duration may have extended. Of course, there is still some uncertainty in these studies, because the complexity of the climate system makes it very difficult for us to completely separate the impacts of global warming from other natural variability. But one thing is certain. In a warming world, the effects of El Niño could be amplified, because a higher baseline temperature means more intense evaporation, a more unstable atmosphere, and more extreme rainfall. When El Niño overlaps with global warming, it could make extreme weather events much more frequent and much more severe. The history of human understanding of El Niño goes back several hundred years. On the west coast of South America, along the shores of Peru and Ecuador, fishermen noticed this strange phenomenon a very long time ago. It happens every few years, around the end of the year. The once teeming fishing grounds would suddenly become completely barren. Dead seabirds would be found drifting on the surface of the sea, and the seawater would turn warm and murky. These ominous signs would often last for several months, dealing a catastrophic blow to the local fishing industry. The local fishermen called this phenomenon El Niño, which means the Christ child or the little boy. There are 2 possible explanations for the origin of this name. First, this phenomenon always appears around Christmas time, and fishermen believed it was a miracle manifested by the Son of God. Though, of course, it was a bad kind of miracle. Second, the fishermen believed this warm current came from the south, much like a little boy from a faraway place. coming to visit their shores. While the fishermen's observations of El Niño were keen and accurate, for a very long time, these observations remained purely based on experience. No one knew what caused this phenomenon. And even less did anyone know that it was intricately linked to the climates in places thousands of miles away, such as Australia, Indonesia, and even China. What truly turned El Niño from a regional phenomenon into a global topic was a group of explorers and scientists in the early 20th century. In the 1920s, British meteorologist Gilbert Walker noticed a strange phenomenon while studying the Indian monsoon. He realized that the strength of the Indian monsoon seemed to be related to atmospheric pressure changes over the Pacific Ocean. When atmospheric pressure is high in the western Pacific and low in the east, the Indian monsoon tends to be stronger. When this pressure difference weakens or reverses, the Indian monsoon tends to be weaker. Walker called this seesaw-like change in atmospheric pressure the Southern Oscillation. Walker's discovery was groundbreaking. For the first time, he linked the climate of the Pacific with that of the Indian Ocean. And for the first time, he suggested that the atmosphere might have remote connections on a global scale. But he couldn't find the role that sea surface temperature anomalies played in it. Nor could he explain the specific mechanism of this teleconnection. In the 1950s, oceanographers began systematically observing sea surface temperatures in the Pacific. They discovered that sea temperatures in the equatorial Pacific did indeed change in a regular pattern. When the sea temperature in the eastern Pacific rose, the sea temperature in the western Pacific would drop, and vice versa. This year-to-year fluctuation in sea temperature had a close correlation with the Southern Oscillation. By the 1960s, American oceanographers Jacob Birkins and Henry Diaz proposed a revolutionary theory that El Niño and the Southern Oscillation were actually two sides of the same phenomenon. El Niño is the oceanic manifestation, while the Southern Oscillation is the atmospheric manifestation. Together, they form a coupled ocean-atmosphere system. This was the initial concept of ENSO. In the history of humanity's understanding of El Niño, the years 1982 to 1983 were a milestone. That year's El Niño was one of the strongest of the 20th century. Yet its occurrence barely raised any alarms. Scientists at the time had not yet established a complete monitoring system for El Niño. There were only scattered buoys and research ships in the Pacific. When the abnormal sea temperature shifts began, scientists didn't even know what was happening. It wasn't until El Niño had fully erupted, and the catastrophic consequences had already surfaced, that people realized an unprecedented climate upheaval was underway. The seawater temperature off the coast of Peru was 7 or 8 degrees higher than usual. Marine life died in massive numbers. Ecuador and Peru experienced unprecedented torrential rains and flooding. Floods actually occurred in desert regions. Australia fell into a severe drought, which subsequently triggered forest fires. The Indian monsoon began acting up. Hundreds of millions of people were affected. Large parts of East Africa suffered through a massive famine. Extreme weather events were breaking out all over the globe, causing immeasurable economic damage and loss of life. The El Niño of 1982 to 1983 gave the world its first real look at the sheer, terrifying power of this natural phenomenon. It also pushed governments everywhere to significantly increase their investment in monitoring and researching El Niño. After that, a global El Niño observation network gradually started to take shape, and our ability to predict the climate took a giant leap forward. If the 1982 to 1983 event showed us just how powerful El Niño could be, then the 1997 to 1998 event really opened our eyes to both the progress and the limitations of scientific forecasting. In the spring of 1997, oceanographers detected the very first early warning signs of El Niño. An international team of scientists used data from satellites, buoys, and ships to successfully issue a warning months before it hit with full force. Governments around the world took steps to prepare, which helped to cushion the blow. But even with that heads up, the 1997 to 1998 El Niño still caused massive destruction. The extreme weather it triggered resulted in thousands of deaths across the globe and tens of billions of dollars in economic losses. This goes to show that even though we can now predict that an El Niño is coming months in advance, our ability to predict its actual impact, especially the specific time and place for extreme weather events, is still pretty limited. That particular El Niño also left behind a major scientific legacy. It made us realize that El Niño can use Rossby waves in the atmosphere to wreak havoc in places very far away. During the 1997 to 1998 event, the Indian Ocean, the South China Sea, and even the North Atlantic have all shown abnormal climate patterns. This further confirms the global impact of El Niño. Today, our human monitoring and forecasting of El Niño have made significant strides. Regarding the oceans, a global network of buoys, including the famous Argo float array, monitors ocean temperature, salinity, and currents around the clock. This data is transmitted in real time via satellites to data centers, allowing scientists to track the state of the global ocean, almost in real time. As for the atmosphere, a worldwide network of weather stations, meteorological satellites, and weather balloons forms a dense atmospheric monitoring grid. This data enables us to track changes in atmospheric circulation and identify the precursor signals of El Niño. Based on these observations and continuously improved climate models, scientists can now predict the occurrence of El Niño 6 months to 1 year in advance, with accuracy significantly higher than it was 30 years ago. Although precise forecasting of extreme events remains difficult, grasping the overall trend has become relatively reliable. However, we must still acknowledge that the climate system is extremely complex, and the occurrence and evolution of El Niño have inherent unpredictability. Even under the best conditions, we can only provide probabilistic forecasts, rather than deterministic predictions. Just like a weather forecast, we can tell you there is a 70% chance of rain tomorrow, but we cannot guarantee that the street in front of your house will definitely be wet. The most direct impact of El Niño is, of course, in the Pacific region. In a normal year, sea surface temperatures in the equatorial Pacific follow a pattern of being higher in the west and lower in the east. The western Pacific, including Indonesia, Malaysia, Papua New Guinea, and the waters in the northern Philippines are warm and deep. Rainfall is abundant, making it one of the wettest regions on Earth. Meanwhile, in the eastern Pacific, including the west coast of South America, the waters are relatively cold. The upwelling of deep, cold water brings with it a wealth of nutrients, supporting one of the most important fishing grounds in the world. El Niño disrupts this delicate balance. When sea surface temperatures rise in the eastern Pacific, the rain belts shift eastward accordingly. The once humid western Pacific region may face severe drought, while the typically arid eastern Pacific coast may be hit with excessive rainfall. The impact of this shift on ecosystems and economic activities is truly massive. For the fishing industry along the west coast of South America, El Niño is a catastrophic event. The warm water blocks the upwelling of cold, deep currents, preventing nutrients from reaching the surface. As a result, phytoplankton populations plummet, fish that rely on this plankton for food die off in large numbers or migrate away. Fish are the foundation of the entire food chain. So when they disappear, seabirds starve to death in droves due to a lack of food. Marine mammals like sea lions and seals suffer greatly as well. The entire marine ecosystem falls into a state of decline. El Niño also alters the distribution of tropical cyclones. In a normal year, tropical cyclones primarily form in the western Pacific. But in an El Niño year, because the sea temperatures in the western Pacific are relatively cooler, tropical cyclones tend to form further toward the central and eastern Pacific. This means that traditional typhoon-prone areas, such as the Philippines and the southeastern coast of China, may see fewer impacts from tropical cyclones, while regions like Hawaii in the central Pacific face much greater risks. El Niño's impact on the Asian monsoon system is one of its most significant global consequences. The Indian monsoon is vital for South and Southeast Asia, the most significant climate event in this region. From June to September every year, moist monsoons blowing in from the Indian Ocean bring the vast majority of the annual rainfall, sustaining the livelihoods of over 1 billion people. The success or failure of Indian agriculture depends heavily on how the monsoon behaves. El Niño is often accompanied by a weakening of the Indian monsoon. Statistics show that, in years affected by El Niño, Indian monsoon rainfall is, on average, about 10 to 20% lower than in normal years. During years with a strong El Niño, this figure can be even higher. A weaker monsoon means less rainfall, higher temperatures, and worsening droughts. This poses a severe challenge to India's agriculture, water resources, and energy supply. From 1987 to 1988, a powerful El Niño caused Indian monsoon rainfall to plummet by 27%. Agricultural production was severely damaged, and tens of millions faced food shortages. 2009 also saw a strong El Niño, and India suffered through a severe drought. Rice and wheat yields dropped significantly. These tragedies keep repeating themselves during El Niño years. Southeast Asia is also affected by El Niño. Indonesia is among the countries most significantly impacted due to the drought and high temperatures caused by El Niño. Forest fires in Indonesia are often much more frequent and intense during those years. During the 1997 to 1998 El Niño, Indonesia experienced one of the worst forest fires in its history. Thick smoke blanketed the entire Southeast Asian region, causing massive environmental and economic losses. The impact of El Niño on Australia is equally devastating. Australia is a continent dominated by arid and semi-arid climates, where most regions receive very little rainfall and fluctuate drastically from year to year. The eastern and northern coastal regions of Australia are relatively humid, supporting the country's main agricultural and population centers. However, even in these areas, water resources remain scarce and precious. During El Niño years, the eastern and northern parts of Australia often see significantly less rainfall, higher temperatures, and increased evaporation, which greatly raises the risk of drought. Drought can lead to crop failures, pasture degradation, and water shortages. At the same time, dried-out vegetation and high temperatures create the perfect conditions for forest fires. In El Niño years, forest fires in Australia tend to be more frequent and more intense. The 2009 to 2010 severe drought brought on by El Niño created the conditions for one of the worst forest fires in Australian history, the Black Saturday bushfires. This fire caused 173 deaths and burned millions of hectares of forest, becoming the deadliest heatwave and fire event in Australia's history. In 2019, Australia once again experienced an exceptionally severe forest fire season, although that year was not a typical El Niño year. Anomalous ocean temperatures may have compounded the effects of El Niño, contributing to the catastrophic fires. Billions of animals perished or lost their habitats in the fires, and entire ecosystems were devastated. The impact of El Niño even extends to Africa, bringing more suffering to that continent. East Africa is one of the most significantly affected regions. In a normal year, East Africa's short rainy season from October to December brings relatively stable rainfall. But in an El Niño year, the short rainy season often sees excessive rainfall, causing floods, and the long rainy season from March to May might see less rainfall, leading to droughts. This disruption in rainfall patterns poses a serious threat to agriculture and food security. Between 2015 and 2016, a strong El Niño brought severe drought to East Africa. Somalia, Ethiopia, Sudan, and South Sudan experienced a major food crisis, with millions of people at risk of famine. The international community was forced to significantly increase humanitarian aid to prevent large-scale starvation. Southern Africa is also affected by El Niño. During El Niño years, rainfall in southern Africa's wet season tends to be below average, affecting the yields of staple crops like corn. Between 2015 and 2016, southern Africa also went through a severe drought and food crisis. It is worth noting that Africa's vulnerability comes not just from El Niño itself, but also from a lack of response capacity. Many African nations lack comprehensive climate monitoring and early warning systems. Agricultural infrastructure is weak, food reserves are insufficient, and social stability faces challenges. When El Niño compounds these vulnerabilities, the consequences are often catastrophic. North America is affected by El Niño more indirectly, but the impact is still significant. For the United States, the effects of El Niño vary by region. In southwestern areas like California, El Niño often brings more rainfall than in normal years. For this chronically dry and densely populated region, this is a good thing, in fact. The strong El Niño of 2015 to 2016 helped California end a severe, years-long drought. But the impact of El Niño on the United States, the impact on other regions is much more complex. During El Niño years, the southern United States, including Texas and Florida, tends to be wetter than in normal years, increasing the risk of heavy rain and flooding. Meanwhile, the northern United States, including Washington and Oregon, may be drier than usual, which raises the risk of forest fires. El Niño also affects winter temperatures across the U.S. In El Niño years, winter temperatures in the southern U.S. tend to be warmer, while the north may experience colder weather. This happens because El Niño shifts global atmospheric circulation patterns, affecting the frequency and path of cold polar air moving south. South America often experiences extreme climatic polarization during El Niño years. The west coast of South America, including Peru, Ecuador, and northern Chile, will, during El Niño years, experience abnormal, torrential rain and flooding. These regions are usually dry with little rainfall, so their infrastructure and emergency plans rarely account for such extreme downpours. When El Niño brings heavy rainfall, it often leads to severe flooding disasters. In 2017, a moderate El Niño caused severe flooding in Peru, leaving over 100 people dead and hundreds of thousands affected. The heavy rain triggered mudslides and landslides, destroying numerous homes and vital infrastructure. At the same time, southeastern South America, including southeastern Brazil and northern Argentina, may experience, during El Niño years, weather that is much drier than in normal years. These areas are the agricultural heartland of South America, and the drought can lead to a sharp decline in crops like soybeans and corn. This north-south split in climate patterns leaves South America facing a two-front battle during El Niño years, fighting floods, while simultaneously fighting droughts, making the allocation of emergency resources incredibly difficult. The impact of El Niño reaches far, well beyond the areas directly connected to it, through atmospheric and oceanic circulation. It affects almost every corner of the globe. On the atmospheric side, the tropical Pacific sea surface temperature changes, triggered by El Niño, generate Rossby waves. These waves can travel vast distances, influencing atmospheric circulation in mid-latitude regions. For instance, El Niño shows a statistical correlation with winter temperatures in Europe and North American winter storm tracks. Although this correlation is not as direct or intense as it is in the tropics. On the oceanic side, El Niño impacts global ocean circulation. Changes in Pacific sea surface temperatures can, through atmosphere-ocean interactions, influence sea surface temperature patterns in the Indian and Atlantic Oceans, subsequently affecting global ocean temperature profiles. El Niño also impacts global carbon cycles and biogeochemical processes. The ocean's ability to absorb carbon dioxide from the atmosphere changes due to El Niño. During El Niño years, the balance between global carbon emissions and absorption may shift. Some studies have even found that El Niño is linked to the spread of certain infectious diseases. Warmer waters and increased rainfall can boost the breeding of disease-carrying insects like mosquitoes, causing the risk of diseases such as malaria and dengue fever to rise in certain regions. In short, El Niño is like a giant lever within the climate system. With just a slight pull, it can trigger widespread and profound chain reactions across the globe. China is located in East Asia, on the western shore of the Pacific Ocean. This geographical position dictates that the relationship between China's climate and El Niño is complex and deeply intertwined. First of all, China is one of the countries most affected by monsoons in the world. Every summer, the summer monsoons from the Pacific and Indian Oceans, transporting vast amounts of water vapor to eastern China, bringing with it abundant rainfall. The Mayu Front, the leading edge of this summer monsoon, is a unique weather system in the Yangtze and Huai River basins of China. And it is vital to the water security of hundreds of millions of people. Furthermore, China is located in the core region affected by El Niño. When El Niño occurs, the sea surface temperatures in the equatorial Pacific change the distribution of tropical atmospheric circulation, which in turn impacts the strength and path of the East Asian monsoon. This means that China is affected by El Niño in a way that is often more direct and significant than most other countries in the world. The impact of El Niño on China is multifaceted and multi-layered. It influences the distribution of summer rainfall. It affects winter temperatures. It impacts the frequency and tracks of typhoons. And even affects air quality. Understanding how El Niño affects China is of great significance for China's climate prediction, disaster prevention, mitigation, and resource management. The most significant impact of El Niño on China's summer climate is reflected in the shifting of rainbelts. In a normal year, as the summer monsoon moves northward, the rainbelt gradually advances from South China to the Yangtze-Huai River Basin, North China, and Northeast China. This process of advancement is influenced by many factors, among which El Niño is an important regulating factor. When El Niño occurs, the western Pacific subtropical highs, position and strength often change. In an El Niño year, the subtropical high tends to be further south and east. This causes the rainbelt to linger over the Yangtze and Huai River basins for a longer period, resulting in excessive rainfall, while North and Northeast China may experience less rain. This is why during El Niño years, southern China especially the middle and lower reaches of the Yangtze River and the Y River Basin, are more prone to flooding, while the north may face droughts. The summer of 1998 is a classic example. That year, a powerful El Niño event triggered a massive flood in the Yangtze River Basin. For an entire summer, torrential rain poured down, almost without pause across the middle and lower reaches of the Yangtze, resulting in a historic disaster. The main dikes of the Yangtze were in critical danger time and again. Countless homes were submerged, and tens of thousands of people were forced to relocate. The floods that year became an indelible memory for an entire generation. 2016, which was also a year following a strong El Niño, saw severe flooding occur in the Yangtze, Y River, and Lake Tai basins, causing significant economic losses. But this time, we had better early warning systems and emergency response mechanisms in place, so casualties were greatly reduced. It is worth noting that the impact of El Niño on China's rainbelts is neither linear nor fixed. The specific location and intensity of the rainbelts are also influenced by other factors, including Arctic sea ice, the Tibetan Plateau, snow cover, the Pacific meridional mode, and more. El Niño is just one of these factors, although it is often one of the most significant ones. The impact of El Niño on China's winter climate is equally striking. The most direct effect is that in El Niño years, winter temperatures in China tend to be higher, increasing the probability of a warm winter. Statistics show that, in El Niño years, the probability of higher winter temperatures in China is about 60 to 70%. Whereas in La Niña years, this probability drops significantly. A warm winter sounds like a good thing. After all, who doesn't love a mild winter? But warm winters can also bring problems. They cause winter wheat to turn green too early, reducing its resistance to cold, which becomes a major risk if a late spring frost occurs. It's easy for freezing damage to occur. A warm winter can also affect the spread patterns of respiratory infectious diseases like the flu. It may increase the risk of disease transmission. Additionally, warm winters are often accompanied by less precipitation, which could lead to droughts in winter and spring, impacting agricultural production. However, winters during El Niño years are not always warm and mild. Sometimes, El Niño can cause cold polar air to move southward more frequently, bringing intense cold waves. This happens because El Niño changes the atmospheric circulation patterns, potentially affecting the stability of the polar vortex. When the polar vortex becomes unstable, cold air can break through its defenses more easily, sweeping down to the south. For example, in January 2016, an extreme weather event known as a super cold wave hit most parts of China. Nearly 90% of the country's land area saw temperatures drop below 0 degrees. Cities in southern China, such as Guangzhou and Hong Kong, experienced rare snowfall or sleet. That year, at the beginning of the year, was exactly the peak of the strong 2015 to 2016 El Niño. So, in an El Niño year, the winter might be warm, or it might be hit by a cold wave. Just how it plays out depends on the intensity of the El Niño and the status of other climate factors at the same time. Another significant way El Niño affects China's summer is through typhoons. Typhoons are one of the most important weather systems affecting China. Every year during the summer and autumn seasons, over a dozen typhoons make landfall or impact China, bringing fierce winds, heavy rain, and storm surges, causing significant losses. El Niño can change the characteristics of typhoon activity in the Northwest Pacific in El Niño years. Because sea surface temperatures in the western Pacific are relatively lower, the formation zones of tropical cyclones often shift toward the central Pacific, and the number of cyclones may decrease slightly. But more importantly, El Niño affects the tracks of typhoons. In years with El Niño, the number of typhoons hitting China is usually lower. But once a typhoon makes landfall, its intensity may be higher. This is because during El Niño years, typhoons tend to spend more time developing over the ocean, giving them more chances to strengthen, while the time spent being weakened by friction with land before landfall is relatively shorter. Additionally, El Niño may also lead to a higher proportion of typhoons turning northward. The proportion of typhoons making direct landfall along the coast of East and North China decreases, while the proportion of those hitting Guangdong and Hainan may increase. This shift in paths provides important insights for typhoon prevention efforts in different regions. By influencing temperatures and precipitation, El Niño has a broad and complex impact on agricultural production in China. When it comes to grain production, the impact of El Niño varies depending on the crop, variety and its growth stage. For rice in El Niño years, the growth period of early rice in South China is often delayed, making it prone to low temperatures during the grain filling stage, which affects yields. And if flooding occurs in the middle and lower reaches of the Yangtze River, it can destroy rice seed beds for intermediate and late season crops, making transplanting difficult. As for corn, drought in the North China region may lead to poor pollination for spring corn, and a lack of water during the growing season for summer corn. For wheat, a warm winter may reduce the cold resistance of winter wheat and increase the risk of late spring frosts. El Niño also affects the patterns of pest and disease outbreaks, as warm and humid winters allow pests and diseases to overwinter more easily, which may lead to more severe infestations the following year. In El Niño years, migratory pests like the brown planthopper and the armyworm might arrive earlier than expected. With a longer season of destruction, the impact on cash crops is just as significant. For example, during El Niño years, citrus-growing regions in southern China may suffer from fruit cracking due to excessive rainfall and an increase in plant diseases. Meanwhile, apple orchards in the north might see smaller fruit sizes due to drought, resulting in lower quality. To better handle the impact of El Niño, the agricultural sector needs to prepare well in advance, including adjusting crop varieties and planting schedules, strengthening agricultural infrastructure, improving agricultural insurance systems, and establishing more precise weather early warning systems, alongside professional agricultural guidance. You might not realize it, but El Niño is actually closely connected to what is on your dining table. Let's start with something as direct as seafood. In a normal year, the coasts of Peru and Chile are the world's most important sources of fish meal and fish oil. These small forage fish support 1/3 of the global aquaculture industry, because fish meal is a crucial source of protein for feed used in farmed fish and shrimp. But when El Niño hits, the fisheries collapse, fish meal production plummets, and prices skyrocket. The global aquaculture industry is then forced to find alternative feed. Costs rise, and eventually that cost is passed on to the consumer. El Niño also impacts soybean production in Brazil and Argentina. South America is the world's most important exporter of soybeans, and a significant portion of the soybeans imported by China comes from there. During an El Niño year, southern Argentina and Brazil often experience dry spells, which can lead to reduced soybean yields, since soybeans are a vital source for cooking oil and animal feed. A drop in production will drive up the price of soybean oil, along with the prices of pork and chicken. Palm oil production in Southeast Asia is also heavily affected by El Niño. Indonesia and Malaysia are the world's largest producers and exporters of palm oil. The drought brought on by El Niño leads to a decline in oil palm fruit yields, causing a drop in palm oil production. Palm oil is the most widely used vegetable oil in the world, from French fries to lipstick. It is an essential ingredient in thousands of products. El Niño can even impact the price of coffee. Brazil is the world's largest coffee producer. During El Niño years, the southern part of Brazil tends to be drier, which can affect the yield and quality of coffee beans. During the 2015 to 2016 El Niño, Arabica coffee prices soared to a multi-year high. So the next time you notice that the price of certain food or daily goods at the supermarket has gone up, one of the reasons behind it might be that thousands of miles away, an El Niño event is happening in the Pacific Ocean. El Niño doesn't just affect our wallets. It also impacts our health. First is the risk of infectious diseases. Climate anomalies triggered by El Niño, including rising temperatures, increased rainfall, and frequent flooding, can change the distribution and activity levels of disease-carrying insects like mosquitoes, ticks, and fleas. Warm and humid environments are ideal for mosquito breeding, and the standing water caused by rainfall provides them with more breeding grounds. Malaria, dengue fever, Zika virus, and yellow fever, and other vector-borne diseases often see an increased risk of transmission during El Niño years. For example, during the 2015 to 2016 El Niño, Brazil experienced a massive Zika virus outbreak, which then spread to other Latin American countries. Pregnant women infected with the Zika virus could give birth to babies with microcephaly. This event triggered a global public health alert. Secondly, there are respiratory diseases. The forest fires caused by El Niño produce large amounts of smoke and particulate matter, affecting air quality. During the El Niño event of 1997 to 1998, the smog produced by forest fires in Indonesia enveloped the entire Southeast Asia region for several months, causing air quality to deteriorate drastically and leading to a surge in respiratory illness cases. Floods themselves also bring significant health risks. The stagnant water left behind after the floods recede is an ideal breeding ground for mosquitoes. The worsening sanitary conditions in disaster areas increase the risk of the spread of intestinal infectious diseases and skin diseases. In addition, the psychological trauma caused by floods can also, in the aftermath, long-term impact the mental health of disaster-affected residents. The warm winters during El Niño years may also affect the transmission patterns of influenza. Influenza viruses spread more easily in cold and dry environments. If the winter is unusually warm, the flu peak might be delayed or weakened. But if a brief cold snap occurs, seasonal flu and respiratory syncytial virus might circulate at the same time, putting pressure on the medical system. Facing the challenges brought by El Niño, humanity is not completely helpless. Scientific forecasting and early warnings are our first line of defense in dealing with El Niño. After decades of development, scientists have become able to predict the occurrence of El Niño months, or even a year in advance. When sea temperatures in the equatorial Pacific begin to rise abnormally, and trade winds begin to weaken, with various precursor signals appearing in the ocean and atmosphere, scientists can issue warnings. Currently, there are several international agencies that release El Niño forecast and monitoring information, including the National Oceanic and Atmospheric Administration, the Australian Bureau of Meteorology, the Japan Meteorological Agency, the China Meteorological Administration, and others. These agencies use satellites, buoys, ships, aircraft, and various other observation methods to collect data and run complex climate models to make predictions, providing early warning information to governments and the public worldwide. But we must also realize that there are still limitations in predicting El Niño. First of all, we cannot predict the exact intensity or duration of El Niño. We can only provide probability-based estimates. Secondly, the specific impact of El Niño on regions like China is even harder to forecast. This is because regional climates are influenced by many more local factors. Therefore, El Niño warnings should be a process that is constantly updated. As more observational data is gathered, and models continue to run, forecasters will keep revising and updating their predictions to improve the accuracy and precision of their forecasts. Agriculture is one of the sectors most heavily affected by El Niño. The response measures in the agricultural sector are worth our focused attention. The first is variety selection. Different crop varieties have varying levels of tolerance to climate stress. In years with a higher risk of El Niño, we can choose to plant varieties that are drought-resistant, flood-tolerant, or heat-resistant. For example, choosing early maturing rice varieties can help avoid potential cold damage later in the season. Choosing drought-tolerant corn varieties can reduce losses during dry spells. The second is adjusting the planting structure. By adjusting sowing, transplanting, and harvest times, we can ensure that a crop's critical growth stages avoid periods with the highest climate risk. However, this requires accurate climate forecast information to back it up. And we also need to consider how this fits with crop rotation schedules. Irrigation and drainage facilities are the key to dealing with drought and flood disasters. In years with a high risk of drought, we must prepare by storing water in advance and developing water-saving irrigation technologies. In years with a high risk of flooding, we need to clear drainage ditches ahead of time and improve flood drainage facilities. Agricultural insurance is an important tool for mitigating risk. Innovative products like weather index insurance can automatically trigger payouts based on meteorological data like temperature and rainfall. There is no need for door-to-door damage assessments, which both increases efficiency and lowers the cost of claims. The Agricultural Technology Extension System acts as a vital bridge, connecting scientists with farmers. By delivering timely El Niño warnings and response advice to farmers, and guiding them in taking appropriate farming measures, we have an effective way to reduce disaster losses. In the face of extreme weather events triggered by El Niño, disaster prevention and mitigation work is the key to protecting people's lives and property. Regarding flood control, we need to strengthen the construction and management of flood control projects, such as levees, reservoirs, and flood storage areas. Improve urban drainage systems, and develop and drill flood emergency plans. During years with a higher risk of El Niño, we must clear out flood control reservoir capacity in advance, step up levee inspections to identify risks, and prepare for emergency relocation and hazard avoidance. Regarding drought prevention, we need to strengthen the unified dispatch and management of water resources. Prioritize the supply of water for human and livestock consumption as well as basic daily needs. Promote water-saving agriculture and industry, and build emergency water supply projects. As drought conditions develop during El Niño years, we must promptly activate emergency drought response measures and organize water delivery to rural areas. The focus of typhoon defense lies in three links: prevention, avoidance, and rescue. Prevention means strengthening disaster prevention projects like seawalls and shelter belts. Avoidance means promptly organizing fishing boats to return to port to take shelter, and relocating people from dangerous areas. Rescue means being well prepared for post-disaster relief and reconstruction. Every successful typhoon defense effort is the result of these three lines of defense working in coordination. Preventing heat waves requires special attention to vulnerable groups, such as the elderly, children, and those with chronic illnesses. Opening cooling centers, strengthening health monitoring, and widely promoting heat stroke prevention knowledge are effective measures to reduce the dangers posed by heat waves. Beyond short-term emergency responses, we also need to consider more long-term climate adaptation strategies. Regarding water resources, we must strengthen the construction of cross-basin water diversion projects, improve our capacity for spatial water distribution, advance the reform of water resource taxes, promote water conservation, and develop unconventional water utilization technologies, like seawater desalination and rainwater harvesting. In the agricultural sector, We need to reinforce the building of high-standard farmland, boost agricultural disaster resilience, and develop facility agriculture. By utilizing greenhouses and similar infrastructure, we can lower climate-related risks, push for large-scale agricultural operations, and increase the capital and technological intensity of farming. Regarding urban development, we need to incorporate climate risks into city planning and management. To improve urban climate resilience, we must strengthen the disaster resistance of city lifelines, such as drainage, gas, and power systems. We need to preserve sufficient green spaces and water bodies to leverage their ecological regulation functions, and build meteorological disaster monitoring and early warning systems to enhance the city's sensing and response capabilities. In terms of infrastructure construction, we need to raise design standards to boost overall disaster resilience. This is especially true for critical infrastructure like transport, communications, and energy, which must be upgraded to withstand extreme events. On this blue planet, the dialogue between the ocean and the atmosphere never ceases. Tropical rainforests and polar glaciers echo each other from afar. A single wave at the equator might, months later, turn into a torrential rainstorm in southern China. The breadth and depth of these connections far exceed the scope of our daily perception. El Niño also reminds us that in the face of nature's power, how insignificant humanity truly is. Even though we can already land on the moon and explore Mars, even though we can already predict the existence of black holes in distant galaxies, yet when faced with the breathing of our oceans and atmosphere, we can only remain humble, listening, observing, and adapting. We may be able to issue warnings, but we cannot prevent it from happening. We can mitigate its impact, but we cannot eliminate the risk entirely. In this era of climate change, El Niño may become even more frequent and intense. We cannot change this trend, but through a better understanding of it, forecasting it, and responding to it, we can reduce the losses it brings. Every successful warning, every effective response, every recovery and reconstruction after a disaster, is a victory for human wisdom. May you have sweet dreams tonight. Good night.